I'd like to welcome Brendan McMahan, who's here from San Francisco, and he works on Federated.
Seattle.
Oh yeah, Seattle, of course. So many SF people, and he works on Federated Learning. So over to you,
Thanks.
Brendan.
Hi, great to be here. Yeah, my name is Brendan McMahan, and I'm going to be talking about Federated Learning. This is work from a whole bunch of people, and I'll try to give some credit along the way, but won't really be able to do it justice. So the overall goal of Federated Learning is really to enable machine learning engineers and data scientists to work productively with decentralized data with privacy by default. So I'll try to unpack that over the course of my talk. I'll start out with a little bit of motivation for Federated Learning, and then talk about the details of what it is and a little bit about how it works. Talk about some of the applications of Federated Learning that we're exploring at Google right now, and then talk a bit about bringing Federated Learning into the broader world, and hopefully have time to touch a bit on Federated Learning and privacy. So why Federated Learning? The kind of fundamental observation is that data is born at the edge. So there's now billions of phones and IoT devices constantly generating data. And that data, when combined with machine learning, really enables smarter products, better products. It can make the world a better place. Another trend we see is that increasingly the processing of that data is moving to device. So think, for example, of putting machine learning models on device to make predictions locally, as opposed to sending queries to a model in the cloud. So that on-device prediction approach has a lot of advantages. You get improved latency, apps that work offline, better battery life, privacy advantages, and so on. But that leaves open a couple of obvious questions. Now, how do we do analytics? How do we do machine learning? Typically, those have required a centralized, kind of fully inspectable data set. So can we move beyond that? So when my team started thinking about these things around 2014, we saw three basic choices. Don't use that data to improve products and services. Centralize the data anyway, even if you're doing on-device inference. Or invent a new solution. And being a privacy-conscious research team at a data-driven company, you can guess which of these alternatives was most attractive. And I think we've been fairly successful. Federated Learning is not a silver bullet. It doesn't apply to all problems, let alone solve all problems. But when it is applicable, I think it has some significant advantages, which I'm going to hopefully talk about today. But first, let's start with what is Federated Learning. Before I can really get into that, it's helpful to kind of start from a baseline of what a typical machine learning workflow in the data center looks like. So we have a machine learning engineer, they have a centralized data set. They don't just kind of train one model and be done. Typically, it's an iterative process, training kind of grids of models to explain different hyperparameters, different model architectures, interspersed with evaluation on held out data. And eventually, you come up with a good model that's a fit for the data set you have in the data center. Then in a production setting, you would typically go into a model deployment workflow. So you perform additional validation to make sure that that final model really is good. And then, and only then, do you start rolling that out to real devices. So typically that would involve some A/B testing, looking at actual user metrics based on how the model is actually working in the real world. And then eventually it would go out to all users. And importantly, that model deployment and validation workflow is going to be exactly the same for Federated Learning. The thing that really changes is the training and evaluation. We want to replace that use of a centralized data set with decentralized data, data that's distributed across maybe millions of mobile or edge devices. But we want the model engineer's workflow to be as similar to what they're used to as possible. So you still train grids of models, you still do hyperparameter search, you still do model evaluation, but instead of having that compute run in a data center on a centralized data set, some of that compute is distributed to where the data is on these edge devices, runs locally on those devices, and then the server aggregates the results. So I'm going to kind of now dive into a little more detail of how one of the core steps in that workflow works, training a model with Federated Learning. So if a device is plugged in on free Wi-Fi, otherwise idle, it can check into the server and say, do you need me to do any work? And most of the time the server will say, not now, come back later. But sometimes if there's a training task that needs to be executed, the server will say, yes, I have some work for you. And in that case, there's an initial model, which the model engineer has specified, and that gets downloaded by the participating device. And that device runs TensorFlow locally on the mobile device, processing its local cache of training data to compute some updated model. And importantly, that updated model is ephemeral. It's not going to be used to make predictions for the user. It's just a temporary kind of artifact of the training process. Its only purpose in life is to kind of produce an update to the global model, which is sent to the server. And that update that's sent to the server is the only thing we're going to send to the server. The raw training data stays on device. So this is an example of the privacy principle of focus collection. We're only sending an update to the server for a very particular purpose. In this case, improving a particular generation of the global model we're trying to train with federated learning. Another privacy principle that comes out here is the notion of ephemeral reports, or essentially retaining data for the minimum amount of time necessary. We don't actually really need any individual update. We aggregate those together and apply them together to improve the global model. So we never need to persist those updates from an individual device. They're kind of immediately aggregated in memory and used to improve the global model. So in practice, this process is happening in parallel on, say, hundreds of devices that are all computing updates to the same version of the global model. Those are aggregated into a new combined model. And then that improved version of the global model is made available to the model engineer. So they can, for example, do additional evaluation on that. And so this is another privacy principle. We kind of want to aggregate as soon as possible. So since all the model engineers needs is the model and not the individual updates, that's all that gets released. Now, in practice, one iteration of this federated training protocol isn't nearly enough to get a good model. Typically, we would iterate this process thousands of times. So we take that first kind of improved version of the model, ship it out to more randomly selected devices, and then those devices compute their own updates based on their local data, and we continue to iterate. Again, intermittently, the model engineer will do evaluation and decide when they've reached a good model. So typical orders of magnitude here, we might use hundreds to thousands of devices per round. We might need thousands of rounds to reach convergence. And each of those rounds might take some number of minutes to complete. So in practice, you're looking at probably a few days to train your model with federated learning. Now, what I've described is kind of the general scheme or flow of federated learning. It's not a particular optimization or training algorithm. And in fact, developing kind of more sophisticated, better optimization algorithms for federated learning is a really interesting avenue for future work. The algorithm we use in practice is called federated averaging, and it's a relatively straightforward variation of stochastic gradient descent, the standard algorithm used for training deep networks in the data center. The difference is that here we're actually going to run stochastic gradient descent on each device locally for a small number of steps, not all the way to convergence. And then the aggregation step is just a simple weighted average. And I'm not going to spend too much time describing this algorithm. You can see more in the paper referenced on the slides. The two things I do want to mention, one is it works surprisingly well. And two, because it's so simple, it makes it quite composable with other technologies, and that's very useful. I'll hopefully talk about some of those other technologies towards the end of my talk. One thing I do want to point out about the federated setting, and this is what led us to coin the term federated learning or federated optimization in the first place, is that this is a dramatically different setting than kind of the traditional distributed learning setting. The primary difference is where the data is stored and how it's distributed, right? We have a decentralized, naturally partitioned data set. No one user's device is reflective of the general population. It reflects that particular user's usage of whatever the app is. So that means the data in technical terms is not identically distributed, and that has some significant ramifications for the kind of optimization algorithms that work, for example. So you can see this in the green plot at the bottom of the slide there. This is a plot of round completion rate for a model trained in the US. And what you're seeing here is that devices generally meet the eligibility criteria of being idle, plugged in and on Wi-Fi at night. And so at night, we have a lot more devices available for training, and we can make a lot more progress. But this also has ramifications for the optimization algorithms. As I mentioned, you can see the ICML 2019 paper there for more details. Another major difference are just the characteristics of these nodes. We want to treat the nodes as anonymous and interchangeable, unlike in the data center. The nodes in federated learning are stateless, they're highly unreliable, they have limited communication bandwidth, and so on. So all of these things need to be taken into account when designing a federated learning system. So we're already using federated learning pretty extensively at Google. Federated learning code is installed on, I think, over 500 million devices, and federated learning workflows are in use by multiple teams on a number of different products, including Pixel devices and Gboard. One of the uses of federated learning we've announced for Pixel devices is in setting search. Pixel devices have thousands of different settings, from font size to screen brightness, battery usage, and so on, that users need to adjust. And by using a federated model trained by actual user interaction with the setting search, we can surface the right relevant settings at the right time to users, producing a much better user experience than kind of the previous hard-coded approaches. Another major application is in Gboard, Google's mobile keyboard. You probably don't think too much about your mobile keyboard, but the fact is you also probably use it a lot every day. And you've probably noticed that text entry is slower than on a physical keyboard. On the plus side, sharing cute stickers is much easier. But under the hood, Gboard is powered by a bunch of different machine learning models that power different parts of the experience. And the team has been working since 2016 to develop and evaluate models using distributed, decentralized data. So the goal of the Gboard team is really to be the most privacy first and the best mobile keyboard available. One of the core machine learning models in the Gboard is a language model. It helps decode the taps and swipes on the keyboard to recognize what you're typing, and it also directly powers the prediction strip, predicting the words you're likely to want next based on what you've typed so far. And this is a great example of an application where federated learning is a very good fit. The first thing to observe is that it's really important to train your language model on data from the right distribution, on representative data of real usage. We could train a language model for Gboard on, say, Wikipedia data, but it would be terrible because people don't type text messages anything like they write Wikipedia articles. So it's very important to train on the right kind of data in order to make good, relevant predictions. At the same time, the data from mobile keyboard usage can be extremely privacy sensitive, right? Think text messages with loved ones, search queries, everything that flows through the keyboard. So doing something that allows us to still kind of extract general knowledge from that data without needing to centralize it is extremely important. The final point is a little bit more subtle, but is quite important for assessing the applicability of federated learning. With next word prediction, we can naturally infer kind of what the correct answer was from user interaction. So if we don't predict the correct next word, the user will tap it or swipe it out manually, and then so we know what we should have predicted, and we can use that to improve the model for next time. So the Gboard team used federated learning to train a state-of-the-art recurrent neural network for language modeling, which they used to replace one of their previous baseline n-gram model. And this led to a really substantial improvement in accuracy, so plus 24% next word prediction accuracy. So this was a really exciting moment for the team. I mean, this is exactly why I'm excited to be working on federated learning. We can deliver really big improvements to user experience in a very privacy-preserving way. And since then, the Gboard team has kind of been on a tear using federated learning to train a bunch of the models that power the Gboard. So I have some links in the slide here to a number of papers that they've put out describing that work. We're also really excited to see increasing interest in federated learning outside of Google, and this is something we've always believed is really important. We just hosted a workshop in Seattle with over 100 attendees, about half from outside of Google, mostly from academia. There was a great tutorial at CVPR. There's going to be another workshop this summer. And we're seeing a rapidly accelerating trend of publication in this area. And I think there's good reason for that. It's a really exciting area. There's a chance for big impacts on the world, and it's also just really interesting from a pure research perspective. One of the things that makes it most interesting is that there's no one approach or one set of techniques that you need. Machine learning expertise isn't enough. We need people with cryptography backgrounds, with differential privacy backgrounds, with fairness backgrounds, compressed sensing, information theory, optimization. So in a lot of fields I'm probably forgetting. All of these things kind of come together, and often the hardest problems aren't kind of centered in one field. They're at the intersection of these different areas, figuring out how we can fit the different technologies together and use them in a single system. So this is just an amazing opportunity to do meaningful collaborative research. One of the other steps we've taken to making federated learning more accessible outside of Google was with the open source project TensorFlow Federated, which we released earlier this year. This is an open project on GitHub. We're encouraging contributions. And it provides a couple of different things. At a high level, there's a federated learning API that has complete implementations of standard federated learning algorithms like federated averaging and federated evaluation. So you can try those out in simulation immediately on your own data and your own models. You can do it in Colab in a few clicks and see how federated learning might apply to problems you have. That FL layer is built on top of a federated core API, which really provides lower level building blocks for expressing pretty arbitrary federated algorithms, that is, arbitrary computations processing decentralized data. So I want to give you a quick flavor of kind of how we're thinking about this. TFF has a type system, and so consider a simple example where each device has a temperature reading. We would think of that as a single federated value with type float32 at clients. So that encompasses not only the representation type, but the placement of the data. So data locality is a first order concept here, because that's really important for reasoning both about system level concerns, but also privacy concerns in federated learning. So for this simple example, let's suppose what we want is actually the average of those temperatures placed at the server so that we can release it to a data analyst. We can do that with a single federated operator, in this case federated mean. So you can think of this as a function that maps those float32 values placed at the clients to a single average placed at the server. So you can think of this as a function, but it's not a function that executes locally in any one place. It's really a building block of a distributed system that's moving data from one place to the other in addition to transforming it. So let's do one more slightly more complicated example here. Now let's suppose that we have a data analyst who wants to compute the fraction of devices whose temperature exceeds some threshold. So you start out with that threshold being a value on the server, so you use a federated operator, in this case federated broadcast, to place that data or a copy of that value on each of the devices. And then you use federated map to run a TensorFlow function on each of those devices. In this case, just comparing the threshold to the local temperature reading and returning a 0 or 1 value, depending on whether the threshold is exceeded. And then you can aggregate those local 0 and 1 values with the federated mean, and that's the fraction of devices that exceed the threshold. So I'm not going to have time to kind of walk through this complete example, but this is basically that full example in TFF code. I think it reads a lot like the pseudocode you would naturally write for this. So it's an expressive, declarative way of describing complete distributed systems. So if this is interesting or might be useful to you, I really encourage you to check out tensorflow.org/federated. In particular, the tutorials, I think, are a great place to start. You can load them in Google Colab, so they fully execute in the browser. You can modify them, start executing things, and trying it out for yourself in just a few mouse clicks. So the final point I want to make here is that we are really interested in supporting federated learning in production outside of Google. So if you have ideas about how federated learning might be useful to you or how you might use this technology, we'd be really interested in hearing about it. So the email address is federated-feedback@google.com. Finally, I want to talk a little bit about federated learning and privacy. Federated learning, the way we've built it at Google, has strong privacy properties built in, but rarely are things as simple as either private or not private. And I think to move the field forward, we really need to encourage a more nuanced discussion about privacy. And I don't nearly have the time to start unpacking that fully today, but I want to give one example of the way we've been thinking about this and a couple of technologies we're developing to provide even stronger privacy guarantees. So here's a complete federated learning setup. We have both federated training and model deployment. The model deployment half of things here isn't actually specific to federated learning. The same concerns arise in data center training. And a natural question to ask here, kind of from a security perspective, is who has access to what data, or who can see what, right? So we can ask on the device, what can the device see? What can the network see? What can the server see? And then what can the engineer see, the model engineer? What's released to them? And finally, what could be inferred from the artifacts that we're releasing to the world, like the final model? So, looking at all these different surfaces, we can see where some of the principles we've talked about already fit in. Encryption at rest and on the wire should go without saying. Ephemeral reports and focused collection come in between the devices and the server, and between the server and the engineer, we have the only an aggregate principle. But let's see if we can do a little bit better. In terms of what the server can see, to run at least the federated averaging algorithm, the server really only needs the sum, or the average of the updates. So can we, kind of using technology, enforce that that's the only thing that the server can see? And so we developed a cryptographic protocol that allows us to enforce that. So the idea is the server can't decrypt any individual user update, but the server can decrypt the sum. So I don't have time to go into the full protocol, but I can give you a sketch of how something like this is possible. It starts by setting up a secure communication channel so that devices can exchange masks of the same kind of dimensionality as the underlying model that sum to 0. And we do this across all pairs of devices. So the report that any one device sees is the sum of its masks plus the actual model update. And any one of those masks is enough to make the overall report look completely like random numbers. So we transport all of those reports to the server and add them up. And now we see that if you add up all of them, and only all of them, those masks perfectly cancel out, and you're left with the true sum. But there's no way to learn anything about the individual reports. So we can formalize all of this. And of course, the hardest part, and why there was a lot of new work needed here, is that, as I said before, these devices are highly unreliable. And so we actually have to make this work even as some devices drop out. But this gives you the flavor of the technique. And one final quick vignette here. Let's think about what the engineer can see and what the world can see. That is, what could you maybe infer from the final trained model? This applies in a non-federated setting as well. So as a motivating example, let's think about this language model for Gboard I mentioned. I said it was really good. Could it be too good? Well, if somebody in the audience starts typing on their phone, Brendan McMahan's credit card number is, and their phone provides the correct completion to that sentence, then we have a problem. Or at least I have a problem. So the privacy principle here is pretty clear. Don't memorize individuals' data, right? We want models that generalize. This is kind of basic machine learning, but it's also privacy. There's a bunch of techniques we can use to prevent this kind of thing in practice. For example, only letting the language model predict from a whitelisted vocabulary so it doesn't learn credit card numbers in the first place. But differential privacy is a really nice technique if you can get it to work, because it provides strong formal guarantees that this kind of memorization isn't possible. And fortunately, again, the basic recipe is pretty easy. The actual analysis to turn this into a formal guarantee is quite a bit more complicated. But the intuitive recipe is that we're going to aggregate across a bunch of users. We first clip each user's update to limit its contribution to the average update. So no one user should have too much impact on the overall update. And then the server can add noise that's proportional or bigger than any one user's update. So any one user's update to the model is kind of washed out by the noise we're adding. But as long as we average over enough users, we still get a valuable signal. So you can formalize all of this. Actually, kind of getting this to work on real models in production is still hard. This is an open research area, but I think it's a really exciting direction. And I think these are examples of things, how we can compose these different technologies is one of the things that makes research on federated learning so interesting. So finally, I wanted to give a quick shout out to our federated learning comic. We think it's really important to be able to explain this technology to people at a lot of different levels, from the very tech savvy to the not very tech savvy. This comic actually is probably targeting people someplace in between. And I think it's really fun. If I'm honest, it's really a much more entertaining introduction to this technology than I've been able to give you. So I encourage everybody to check it out. And I actually have a few hard copies with me. So at the next break, I can give those out to at least a few people. Thank you very much.